Hey class, here is our lecture on surface integrals now over vector fields instead of just being parameterized surfaces. Now we're taking surface integrals over actual vector fields. And the first thing that I want to point out is that if that vector field represents some fluid flow, meaning like the flow of water through a river or something like that, then the surface integral, so SI is my abbreviation for surface integral, calculates the total amount of fluid flowing through the surface per unit time. So what that means is you could like almost bend a wire in any shape that you wanted and consider it a surface, almost like a butterfly net. And if you had water or some fluid flowing through a vector field, then if you computed the surface integral, whatever answer you get is exactly the total amount of fluid that went through that surface. And that surface is just some sort of a net, basically. So with line integrals, this is just a reminder because the surface integral is just up one dimension. So flux in there, it used a very special vector field in that case. Remember, anytime we write a vector as E sub n, it's automatically a unit vector. And so that's why I'm dividing by the norm right there. So E sub n is the sub n for normal vector, E for unit, and then at that point t in time. Then flux across a curve in space is using this very specific normal vector there. If you take that line integral and compute it, you will get the total flux, or what crosses that wire in per unit time. So then like line integrals, we do need an orientation. So an orientation is just a choice of like the positive side. So if you have a function or a surface that looks like this, you could designate that up is the positive orientation, and down would be then the opposite or negative orientation. And so then we usually use E sub n at P to represent the positive normal vector, and negative E sub n at P to be the opposite orientation or negative orientation. So then if E sub n is an outward pointing normal the sphere of say some sphere, then the flow rate from inside the sphere to outside is positive flux, meaning they usually call that a source, meaning you took some surface, like say in this case you have a sphere, which is a perfectly fine surface, and if you had an outward normal on that surface and you had a vector space flowing, it would actually be positive because you're flowing in the positive direction from the inside out. If the flow rate is from the outside of the sphere to the inside of the sphere, again, with an outward pointing normal, but now the flow rate is coming in, it's sort of like doing negative work. And so then that is negative flux. So then the normal component of the surface at P for that vector field is just the value of the vector field at P, that vector, dotted with whatever the normal vector is. So that gives you that component of it. And you know a dot product, it should be the norm of f of P, the norm of En times cosine of theta. But En is a unit vector, and so its norm is just 1. And so I don't need it there. That's why that's the only magnitude that shows up in there. And so then a vector surface integral, and it's very important, so important, as a matter of fact, that I brought this in here. If I go back a section in the previous section, here is the surface integral right here. And notice you have a scalar function, a parametrized surface, and then that's the magnitude of that normal vector, and the domain comes from wherever you project the surface down onto the floor, or whatever. And if you take the function to be 1, then you actually compute the area of a surface. The thing that I want you to see in here is just like with scalar line integrals, There is no dot in between those. In here, there's no dot, and it's a little f. Notice in here, there's always a dot in there, and this is now a capital F, where before it was a little f of x, y, z in there. Now we have a capital F and a dot. And so because we want the normal component of that surface at P with respect to the vector field, then we define that surface integral over a vector field to be the scalar. Now notice there's no dot in here. And what happens when we dot two vectors? So F is a vector, E sub n is a vector, and when you dot two vectors together, you wind up with a scalar. Since you have a scalar value, then this is just a single function, just like we did in the beginning when we first learned how to do multiple integration. So that is what is pointed out in here. That's why I darkened that dot right there. Anytime you see a dot, and especially a capital F, that should scream that it's a vector version. Notice this is exactly the same. And whatever the value of this is called the flux across S or the flux through S. Okay, so then this is just a repeat of things that we already have talked about in past notes and videos. A parameterization of that surface is called regular. If the normal vector is never zero, the normal vector doesn't vanish. If the normal vector vanishes, then you don't have a tangent plane there. If you don't have a tangent plane, you don't have a normal vector, and so it doesn't work out. Also, if it's zero, you'll divide by zero. That's not the reason it can't, but it's supporting evidence of that it's not allowed. So then, if this is the normal vector for it then, and again, we do it exactly the same way. You can see down here in it, we take t sub r, t sub s, and we cross them, and then that gives us the normal vector. So we will parameterize a surface, we will find a normal vector, and then this symbol here, again, there's a dot in there. This is the way it's defined as a scalar line integral. So that is from the last section. Notice there's no dot in there, and there's a norm there. That is the same as this right here. So we have some scalar function, we have a magnitude, and then we have our differentials there at the end. So in that, there is a scalar function. That's like the f of x, y, z in there because it's a dot product. There's the magnitude, and there's our differentials at the end. So this is a parameterized surface integral, but we're using the scalar function to be that normal component of that surface with the vector field. The nice thing about this is because E sub n, we defined it to be n divided by the norm, we get these two norms that cancel out, and once again, it turns out to be way easier to do a vector surface integral than it does just a parameterized surface integral. And that's because in the regular parameterized surface integral, you always have that magnitude in there. And that magnitude is the square root of something squared plus something squared, and so on and so forth. So you'll always get a square root in there. So this is a lot easier to compute. Now, I gave you this assignment in there, and if you look, this is problem 6, exactly the way that it's written in there. And so in my notes, this is my solution to number 6. So they give us the vector field, they give us the r and the s. So just so we go back in here, you can see there's my vector field, there's my parameterization, they give me the bounds for it, and they tell me which way the positive orientation is, and so I want to do TR cross TS. So here, there's all the information that was given to me. There's the oriented by. So when I plug the parameterization into the vector field, it's e to the z, that's e to the r, then it's z, that's just r, and then it's x, and x is rs. And so it's as easy as you can to just plug those in. That needs a z right there, and the z is r, so it's e to the r. Need a z right there, z is r, so we put an r there. And I need an x last, the x is rs, and so I put that in there. Okay, once I have that, I can figure out what is the tangent vector in the r direction and the s direction. So I'm going to use this. So if I take the r derivative, that'll be s, 1, and 1. And if I take the s derivative, it'll be r, 1, and 0. And so there we have it there. When you cross it, that's what I get. And now up here, I need to do the f of g, which I have right here, dotted with n. So it really is f dot n in there. And so I have my f, I have my n, and so when I do that dot product, we get e sub r time, or e to the r times -1, that's negative e to the r, plus r times r is r squared, plus, and that's going to distribute, so rs squared minus r squared s. And so there's that right there. Doesn't matter which way I do the integration. So I put the r and the s in, and notice from the parameterization, I can pull out those values, and they become my limits of integration. So if you work it out, it comes out to be 4/3 minus e, which is approximately negative 1.38495. All right, problem 8. Again, if you go in here, here is problem 8. They've changed the normal on us. We've got a sphere now. We've got not even a regular sphere. It's sort of like a weird lopped sphere. And so let's see what we have in this case and how we would go about solving it. I just closed it on accident. So here we go. So on this, there is the vector field. And again, trust me, I've taken, there it is, x, y, z, and so on and so forth. So all of this information was what was given in the problem. Because we're on a sphere, I instantly use that spherical parameterization. And so I'm going to use, it's supposed to be r and r and r, but in that case, r is 1, because this is just a unit sphere. And so there's a 1, 1, and a 1 there. The normal vector, again, how do I get this so fast? If you want, you can do g sub theta and g sub phi, and then you can do g sub theta cross g sub phi to get that normal vector. But all the way back on page 1, I told you here is a cone, here is a cylinder, and here is a sphere. And then later on in there, we computed that. And I said this when I did the other video, and I wrote it in my notes. It's a big deal that this is needed later. And so that will help me. Nope, yes, no, yes. So that's where this comes from, is that other part. This is what it would really be, and so on and so forth. So now what I need is I need f of g. So I need to plug these in here. Well, look, if you look, f just is g, because the x goes in the x, and the y goes in the y, and the z goes in the z. And so when I do that, we're going to have this dot product here. That dot product works out to be this, especially because, you know, the scalar pops out, and then e sub n dotted with e sub n. Remember, v dot v is the norm of v squared, so that's where that comes from. And we're left with that value there. So then now I can get my bounds on this. And here's the thing, I didn't draw this in here, But if z goes from a half to root 3 over 2, those are two heights right here. And so we're actually kind of finding this weird lopped off dome, like somebody cut right through there and right through there, and we're looking at from the side, it would look like this piece. So that's what we're working on. So, but since I know z is those two values, and I know z is cosine phi, I can say, well, if cosine phi is a half, well, when is cosine a half? Cosine's a half at 60 degrees, or pi over 3. And when is cosine root 3 over 2? Cosine is root 3 over 2 at pi over 6. And so, in that case, here's the thing. This, in my notes, originally was a 3 there and a 6 there. That's what pulls that negative. Remember, if you have the integral a to b of f of x dx, that's negative the integral b to a of f of x dx. And so if you switch the limits of integration, you take and pop a negative sign, and those two negatives. Here's another example of a flow rate through a velocity vector field. And so you have some velocity in there, and so they give us the velocity field. That is a vector field right there. They tell us we're on an ellipse. Now, an ellipse wasn't one that I had on the first page, but an ellipse was in there before in the notes earlier in the term. And so remember, it was the a, because it's usually x squared over a squared plus y squared over b squared equals 1. And if you change the a and the b out front, that pulls it from a circle. Remember, if those are both the same, then that is a circle. So in that case, that's what we have for our parameterization of an ellipse in the xy plane. So because we're in the xy plane, I know that my z is always 0. So this is my parameterization all the way back from the first week or so of class. Once I have that parameterization, now I've defined my variables to be r and theta. And with that r and theta, I need to compute t sub r. And so the r derivative of this is 2 cosine theta. The r derivative of this, 3 sine theta. R derivative of that, 0. The theta derivative, that's going to give us a negative sign. This will give us just a cosine, and that's still going to be 0. If I cross them, I get that. Notice all we're gaining from that normal vector, it's pointing straight into that z. It's just pointing straight up with a length of 6. And so that vector, it kind of makes sense that if we're on an ellipse, that vector should point straight north there. So there's my normal vector. If I feed my parameterization into the vector field, now remember, my vector field is this right here, and my parameterization's right there. So the 2r cosine theta should go first, the 3r sine theta should go second, and then we should get, if I square and multiply these, it's going to be like 6r squared. Yeah, right here. So, and then when I dot the two, I get a lot of zeros and zeros, and then that comes out to be that piece. Now what I need is, and notice before I did that, so now I have my scalar function in there, but what I really need is to know what are my bounds for this ellipse. And so in there, what I'm going to do is I use my conversion. I know x is 2r cosine theta. I know y is 3r sine theta. That is from, not there, but my initial parameterization right here. So I plug that in, and I get, sure enough, the r squared pulls out. Cosine squared plus sine squared is 1. So r squared's less than 1. R squared's always positive, so it's bigger than 0. Less than 1, I get my r bounds out of that. And then it said in here, Okay, so we needed x and y both to be positive. And so, even though we had that, you see this is the only spot where they're both positive. X is negative in quadrant 2, they're both negative in 3. Y is negative in 4, they're only there in 1. That means theta starts at 0 and runs to 90 degrees, or pi over 2. So that's where those come from. And when you work that out, I cheated in the integration, but there's what you get. And because there were units in here, meters per second, and this is a volume, a total volume per unit time, then it should be meters cubed per second in there. And so there you have it. That is where this comes from. And just notice that every bit of this hinges on what is that parameterization? What is that parameterization? Back here, what is that? In this case, they gave it to us, but we always need that parameterization first. I can let that kind of slide, and I don't even think about it until I get down to here, where I really have to and that's why in this one, I kind of went about my business, and then right when I got to here, I was like, oh, come over here and let's figure stuff out. Down here, as soon as I didn't pay any attention to my bounds in here, nothing up here, even in here, right when I got to here, I was like, I need to figure out those bounds. And so I draw my piece in there and I figure out using everything within my arsenal. I'm making substitutions, I'm getting bounds for R, I'm figuring out what all these pieces actually mean. The other thing is, it says oriented in the positive z direction. This is oriented already, just pointing straight up in the z direction, and so for that reason, it has the correct orientation. And so there you have it. All right, hang in there, guys. Like I said, the one thing I think that makes this the hardest is parameterizing that surface. And once you have that, it's just get the bounds, plug it into the vector field, and then dot it with the normal vector. And the normal vector, you just have to do a cross product. And the more you do, the quicker you're going to get. So that should help you and get you through. And I'm excited to see how you guys do. Take care.